This morning, we're going to talk about stacks and queues. These are some fundamental data structures. Fundamental as in root to many computer science things, not as in fun. Although actually they're kind of fun because they're pretty simple. This will be a very quick lecture, very short amount of slides. They're up on your dashboard, by the way. And then we will do some live collaborative coding. We are going to code a stack collaboratively when I'm done with the slides. So what is a queue? Well, very simply, a queue is a data structure in which you can add things to the back, and then you can remove them from the front. So adding something to the back is called enqueue. Removing something from the front is called dequeue. So there's enqueue, there's dequeue. And then finally, you can look at whatever item is in the front. So usually that'll be a method called like front or peek. And so that sort of makes a queue like a less powerful version of a linked list, or maybe like an array. So there are many instances where queues will be very useful, not the least of which is programming interviews. Technical interviews love to throw problems at you in which you have to try to think about what data structure best to use. And very often the best data structure to use that will make your life the easiest is a queue or a stack. So they're very simple, but it's still very important to know them. So queues are called FIFO. First in, first out. So the first item you add to the queue is the first item that is removed from the queue. So if I add 1, 2, 3, 4, 5, then when I dequeue, I get 1 out first. So a queue is basically just like a line when you're waiting in line at the taco truck to get tacos. You're waiting in a first in, first out data structure. That's what a queue is. So pretty straightforward. So now let's talk about the time complexity of those operations, enqueue, dequeue, first, and how much space in memory a queue occupies. So how much space in memory does a queue occupy? Yeah, Josh.
N or like O.
Yep, big O of n. Why is it n? Right, because there's n items, we have to store every item at least once, so that makes it big O of n memory that it occupies. Okay, how about the enqueue operation? What time complexity do we think that is? Josh again. Okay, why do we think that?
Because you're just adding it to the back. It's very simple, like
Exactly. It's the same as appending on a linked list at the back if you have a tail pointer. Basically, all you have to do is make sure that you have a pointer to the back element, and you can enqueue in constant time. If you did this with a singly linked list without a tail pointer, it would take n time, but then that would kind of defeat the purpose of the data structure when you can do it much faster. All right, how about dequeue? Yeah. O of 1, yeah. Why? Right, so assuming we have a head pointer and we can look at the item in the front, then it should be O of 1 because we can just grab the item from the front. All right, so this is pretty easy so far, which is great. It's an easy lecture. Let's not stretch our brains too much on Friday morning. And then finally, to look at the item in the front, well, it's the same as dequeuing, just we don't remove it. We just return the value, also O of 1. Okay, now let's talk about stacks. Stacks are a very important data structure. The way your processor works actually uses a stack to keep track of what code it should do next. So basically, every time you call a function, that function gets put on the top of your processor's stack, the list of things it has to do. It executes that function, then when it's done, it pops that function's code off the stack, and then returns to what it was doing previously. So that's interesting. A stack, basically you just push items onto the top, and then you pop them also off the top. So you can only access the top item, and you can also look at the top item the same way you can look at the front item in a queue. And in stacks, this is normally called peek. But it's very important to remember that stacks are last in, first out. So the last item to get added to the stack is the first item to be removed when you pop. So queue, first in, first out. Stack, last in, first out. OK, so what is the space complexity of a stack? It's not a trick question. Yeah, Elliot. Sorry? N, yeah. Same as a queue, we have to take 1 unit of memory for every piece of data we're storing. All right, how about to push something onto the stack? Yeah, Ignat. O of 1? Yeah, just add it to the top. We have a pointer to the top element. How about to pop an item off the stack? Also O of 1? Same thing. And to look at the item on the top of the stack. OK, also O of 1. So stacks and queues have some optional methods. Those we just defined were kind of like the main methods that you'll see in a stack or a queue. Sometimes if they're not dynamic, if they're static, as in if your queue or stack can only hold a fixed number of items, in those cases you'll want methods like isEmpty and isFull. Well, isEmpty can be used in any case. That's a handy method to have. But isFull is handy in the case where you have a static, fixed amount of items you can store in your stack or queue. And that's important so you know if you can add more items or not. Finally, a nice method to have is size, which basically just returns the number of items in the stack or queue. So there's 2 ways to implement size. If we implement size such that we have to iterate through the whole data structure and count, what is the time complexity? Yeah, Ignat. O of n, why? Exactly. So it's O of n because for every element n, we have to look at it to count it. But if we keep track of the size as we're pushing and popping or enqueuing and dequeuing, in that case, we can have size be O of 1 because we can just keep a little variable in memory that knows how large the queue or stack is, and we can just return it immediately when the stack or queue is asked about its size. OK, so in Python, it's trivial to implement a stack with a list because list gives you push and pop, basically. List actually gives you append and pop pops off the back, append adds to the back. So using append and pop with a Python list, you have a stack. And you can read about that in the documentation here. But what about queues? Well, actually, you can't implement a queue with the Python list. Because remember, the Python list is actually a hybrid array linked list. And the arrays are static. It has to reallocate memory every time you grow outside the size of the current array. And also, adding things to the front. Well, so every time you would remove something, dequeue from the front of a Python list, it's going to have to shuffle everything behind it forward 1 space in memory. So that's why it's a really bad idea to implement a queues with a list. You can read about that here in the official docs. So thankfully, there's a Python data structure called a deque, spelled D-E-Q-U-E, that can be used as a queue. So there's a data structure designed to be used as a queue. Yeah. Oh, sorry, looked like a question. OK, cool. Yes, Ignat. Yeah, so very good point. If we were to implement our own queue or stack, how would we do it? What would the underlying data structure actually look like? Ignat's saying, shouldn't it look like a linked list? And the answer is, yeah, that's a great way to do it. Yeah, Aman? It could also be an array. So certainly in the case of a stack, so there's a problem though, right? It could be an array, but arrays are fixed in memory and have an order. So every time you, OK, so arrays definitely could work with a stack, but not in the case of a queue. Because in a queue, every time you add something to the end, that's easy. You can just append to the end of the array. That's like a constant time function. But every time you dequeue from the front, you remove the front element, you then have to take the rest of the contents of the array and shuffle it forward. You could get really fancy and like have a pointer to the actual first item in the array and have blank spaces at the beginning. That's certainly possible. You could do a queue that way. OK, so that's it for the slides. Really quick and easy. Now we are going to attempt to live code a stack. So I'm going to close this. I'm going to open my editor. I have some stack stuff here. I'm going to just straight up delete it. All right. So I have this class stack. I have a couple of very simple test cases in the main method here. So let's start coding stack. What methods do we need in our stack class? Tell me the methods we will add. Yeah, Ignat? OK, so we'll add push, def push, self. What else? Yeah, Kevin. Pop, yeah. Def push, self. Right. OK, what else? Yeah, Hunter. Peek, all right, def peek. Yeah, Ignat. Size, sure. Def size. What else? Yeah, Hunter. String method. That is a good one. So down here, we are actually like printing out our test stack, but that won't actually print anything useful unless we override the string method so that we can define what kind of data we want to be dumped out when we use the print method. So what else? Yeah, Ignat. Is empty. That's useful. All right, so this looks pretty good to me. Let's start implementing this. So the first thing we need to do is create an init method so that we can initialize some of the stuff we're going to need in our stack. So what do we need in our stack? First of all, how are we going to implement this? Does anyone have any idea? Should we do what Ignat suggested earlier and make a linked list? By the way, if you want to follow along in your computer, you probably should. It is some good practice, yeah. OK. So an array. Which, by the way, if we wanted, we could just use a Python list. But then that would be super easy. Every single one of these lines of code would actually just be one line, every single function. So let's not do a list. How would we do it with an array? Wait, what? Oh, an array versus a list? There are some differences. OK, so basically you're saying we could do it with a list. OK, we definitely could do it with a list. Let's not do it with a list so that our implementation, we have to do more of the actual work. Yeah, Eliel. Right. Let's use a linked list because the size can be dynamic. We can have as many elements as we like. We don't have to reallocate memory. And because the items we add can be different sizes too. So if we're going to implement this in the style of a linked list, we're going to need another class. We're going to need a node class. So what is going to be in our node class? So So we're going to make our stack like a linked list, and we're going to have data pointers, that kind of thing. So what are the two items we need in our node class to make this work? Yeah, Adrian. Yep, data and next. So self.data is equal to none. Self.next is equal to none. Okay, there is our node class. It's that easy. So now let's talk about what we need to do in the init of our stack. What sort of things do we need as instance variables inside this class? Yeah. Okay, so like a head pointer like we had in the linked list. Do we need a tail pointer? Remember, this is a stack, not a queue. So stacks are last in, first out. So we push to the top, and then we pop from the top also. Exactly. Okay, so self.head is equal to none. What else do we need here? Yeah, Kevin. A max size? Sorry? The length. Okay, so size. So do we need a max size, given the fact that we're going to implement this with nodes kind of like a linked list? And the answer is maybe not, because we can just keep on adding nodes and reassigning pointers, and it can grow as large as we want it to. Okay. So let's implement size first, because that's super easy. So we have size here as an instance variable. Well, we assume if we calculate size correctly throughout the thing, we can just return self.size. So that was easy. What about is empty? Well, there's two ways we can do it. We can check if size is equal to 0, or we can check to see if the head pointer is none. I think checking to see if the head pointer is none is probably slightly better. So we can just say return self.head is none. So if the head is none, then it's empty. Otherwise, it's not. All right. So now let's implement push. How are we going to do it? Sorry? Append? Okay, so if we were using a list, it would be as easy as just append. But because we're implementing it ourselves, we have to do a little bit more work than that. We have to mess around with this head pointer, and there has to be some logic in here. Yeah, Ignat. Oh, that's a great point. So to push stuff, we need to have something to push on top. Yeah, Unati, you had? Okay, so check if it's empty, if self.head. Uh-huh. Okay, so let's put the new node at the top, because we're going to be using it a couple times. And don't need this. This is some of my Objective-C showing. Okay, so if self.head. Okay, so let's put the data into the node. So if there's something in self.head, we need to make the next equal to new node. So that sounds great. Yeah? Mm-hmm. Mm-hmm.
Assign the new node as the head,
Mm-hmm.
and then the node's pointer to self.head. It doesn't really matter if self.head is empty or not.
Okay. So that sounds cool. So why don't we say, so maybe we can say next node is equal to self.head, and then we can say self.head is equal to new node, and then we can say self.head.next is equal to next node. And then in that case, maybe we don't even need to check if self.head exists. Maybe the logic works in the case where self.head is none and where we have an existing self.head. So let's try that out. So let's see. We have new node is equal to node, so we create a new node. We add the data to it. Excuse me. We grab a reference to our current top element, self.head. We assign the new node to be there, and then we say the next element from self.head should be the former first element. Okay, what do we think? Does that look like it should work? Yes. So the way we're going to implement our stack is using sort of like a head pointer, and we're just going to have it point to the beginning, and then we're going to pop from the beginning also. And so when we add, we're just going to reassign the new item to be the new head, and it will point to the former first item. Yeah. Oh, good point. So we better increment our size variable to make sure we're keeping track correctly. Okay. So now let's implement peek, because peek should be super easy now. How can we implement peek? Any ideas? Yeah, Josh? Let's just return, well, should we return head? So this is a good point here. If we return head here, we're returning a node object, which hopefully anything interacting with our stack doesn't understand the internal implementation and doesn't know that there's node objects even involved. Yeah, Leslie. Yeah. Great point. So we want to return head.data, but we should check if it's empty, because if we try and return self.head.data and our stack is empty, that's going to crash because we're going to try and dereference the data pointer in a none object. So we can say something like if self.head return this thing here, else return none. Yeah. Okay, so can we implement isEmpty and just check that? Well, we have implemented isEmpty, so we could. I don't mind either way, but we could do something like if self.isEmpty, and then here we would have to return none. Otherwise, we can return the data. Yes. Okay. How do we implement pop? Remember, it has to delete and return the first element in the stack, the topmost element. So how are we going to do it? Bueller, Bueller, Bueller. I'm starting to feel like I'm old because maybe 25% of you understood the reference. Yeah, Dan. Okay. So why do we do that?
So that if there's a second node, then change the head to the second.
So Dan's saying we need to check to see if there's a second node after the head, so that if there is, we can reassign that to be the head. But I posit, just how we did it in push, that there's probably a way we can implement the logic where we don't even need to do an if conditional, and we can just do it whether or not the second node is empty or not, whether or not it's none. So how could we do that? We do. We do have to check to see if the list is empty to begin with, so we can do something similar to peek. If self.is empty, return none, else. So now what can we do here in this else? It's looking dead out there. Just looking real dead out there. Don't make me do the kind of thing Evan does and make you get up and all like stretch and wave around. Yeah, Dan. Okay, so we could access self.size and do some logic there. Again, I posit that there maybe should be a way we can do the logic where we don't even need to check either the size or the second element. Yeah, Leslie. Okay, so maybe we'll call it first element is equal to self.head. So then set head to first element dot next. And then return first element dot data. That sounds okay. And let's decrement the size first. No. So the question is a good one. Do we have to clean up memory in Python? The answer is no. Python is a garbage collected language, like many newer scripting languages, and like languages like Java, actually. So garbage collection kind of became a big thing with Java, and it continues to be a very popular way to manage memory because, as the developers, for the most part, we don't have to worry about it. So garbage collection is this thing where it kind of searches through all the objects that we've ever created, and if it finds we're no longer using a certain object, it will delete it. So that's really nice because it means as developers, we don't have to be allocating, deallocating memory, and like manually destructing objects. It does have some performance penalties though. So you'll pretty much never find, for example, a game written in a garbage collected language, certainly not like a AAA 3D game, because performance is so important for games. So game engines often use different ways to manage memory, usually something called reference counting, which we'll talk about when we get into Swift and Objective-C, how reference counting works, because both of those are reference counted languages. So garbage collection is really great. It saves us a ton of time and effort having to think about which objects should still be alive and which should be deallocated. But every so often, the garbage collector actually has to run. And while the garbage collector is running and searching through and deleting unused objects, it actually completely pauses execution of our program. And so that's like a very common problem on Android. Because most Android apps are written in Java, Java is a garbage collected language, sometimes if you're in the middle of an animation or something, you'll see a little stutter because it actually paused the complete execution of your program to go through and do the garbage collection. And that's something that Android developers have to fight and has caused much angst. Me included, I wrote an Android game. I wrote it in C++, so C++ is not a garbage collected language. I had to do all the memory management myself. But it's still wrapped in a Java layer because every Android app has to be written in Java. And so even then, there are still occasional stutters from garbage collecting, so for example, a normal garbage collection on a newer phone might take like 13 or 20 milliseconds. A normal frame in a 60 frames per second game is 16 milliseconds. So very often it'll cause the game to stutter as a couple of frames are dropped while garbage collecting. Yeah, Imad. Mm-hmm. Okay, so at no point did we actually delete the node that is the first element. That's a really good point. So that's part of why garbage collection is magic. What we did do was we reassigned the head pointer, and it no longer points at the first element. So when the garbage collector runs, it's going to see that the first element actually is no longer referenced anywhere by any other object or by our stack class. So no node is referencing the former first element, and our stack class is not referencing the former first element. So that means it's kind of just alone, floating out in the middle of nowhere. And because nothing is referencing it, it can no longer be accessed. There's no way to get back a reference to it. So that means it's not possible to be used anymore, and that means the garbage collector will delete it. When does it happen? Who knows? It's totally up to the implementation of Python to decide when garbage collection happens. Yeah, Ignat.
Isn't there like a del in Python?
So the question is, isn't there a del in Python? I'm not sure, probably. There's probably a way to delete it ourselves.
Is there any reading like, or just like, I think there's like dels, I think it just removes the reference.
Yeah, so there's probably a way to do it, but actually that would not be Pythonic. Python is a garbage collected language, and it's proud to be it, so you should not be like manually managing memory for the most part. You should just let the garbage collector handle it. Okay, cool. So it looks like actually, with the exception of the string method, our stack is now implemented. So how would we implement the ToString method? So the ToString method should return a representation of our stack in the form of a string. So for example, down here, when we do some testing, we call print test stack. So I create a stack called test stack, and then we print it. And we're printing it basically just to look in the terminal to see if it's working correctly. So it should return a string representation that humans can understand and use to reason about the implementation of stack. Yeah.
Well, you would need like a while loop.
Okay, we would do a while loop.
You first create like push the pointer to the head, and then say, well, the pointer isn't none.
Uh-huh.
You print the pointer,
Mm-hmm.
and then the pointer's data, and then like say the pointer is next pointer.
Okay, so Ignat's saying we iterate through our stack following the next pointers, and we print out the data. And that sounds good to me. That's the correct logic, but we do want to make sure that we're not printing out the data. Instead, we're appending it to a string so that we can return a single string as the result of calling this method. So let's do that. Let's say current node is equal to self.head. And then let's say while current node is not none, and let's also create a string. So return string is equal to empty string. And then let's say return string is equal to return string plus current node.data, and we want to make sure that we get the string form of that data, so I'm going to wrap that in a call to str, which will convert any primitive type we put into it into a string. So what are we doing here? We have assigned current node to head, and as long as current node is not none, we can continue grabbing data out and iterating. So we could. Instead of doing return string is equal to return string plus string, we could make it slightly simpler and say something like this. I'm no positivity, Dan. Yeah. Sorry, what? Oh, thank you. Good catch. Okay, so then after we construct the string, we can return it.
Change the pointer, right? Your string adds the data, and then you say current node equals current node dot.
Right. So we have a bug. At no point in our while loop, do we actually change current node? So this would actually be an infinite loop here. So what we have to do is say current node is equal to current node dot next.
Also, you could probably do some fancier formatting with the return string to not just like really append the data to the string, but get some common spaces.
Okay, so maybe we can do some fancy formatting to our return string. Right now we're just adding all the data. So if, for example, like down here we add ABC to our stack, then it would print CBA, but there would be no spaces. And if we had multiple elements of varying sizes, we wouldn't actually be able to tell where each element starts or stops. So let's make return string equal to return string plus the data plus a space in there. So let's add, you want a comma? I don't want a comma, but we could. We could do a comma. And if we did, it would be something like that. Okay, so we think we maybe implemented a stack. There may or may not be bugs, but there's only one way to find out, and that's to use our way too small test case to exercise it to see if it works. So when you do this, which by the way, you'll be implementing your own queue as part of the Markov chain generating sentences section of the Twitterbot tutorial. When you implement your own queue, you might want to do it in a similar way, but you'll definitely want to exercise it more by doing more in the test area of the main function, where you want to make sure you're calling every method, every function of your queue class, in this case the stack class, and you also want to make sure you call every function in like every state you can get the queue in. So you want to call every function if it's empty, see what happens. You want to call every function with only one item. Like you have to think of all the edge cases and test for it. Because if you don't, it's going to make debugging your Markov generated sentences much more difficult. So in general, when you're implementing something, you want to do as many tests right here as possible to convince yourself that it actually works the way you think it does. Okay, cool. So let's go over to our handy terminal. And let's make sure I'm in the right place. I am. So let's see if I can make this bigger. Okay. So let's say python3 stack.py. Oh, look at that. We did it the first try. That's actually pretty amazing. So the test case, I push A, then B, then C, and then we print it, and we can see that we printed out CBA. So A went in first, but then got pushed down as we pushed B and C. Then we can see I popped C because we call pop on C. And then now when we print out the stack, it's only B and A. So cool. We made a stack. We did not test it properly. Probably we should, like after we first create it, like figure out size is equal to test stack dot size, and we should probably make sure all that stuff works, et cetera, et cetera. But hey, we made a stack on the first try. That's pretty cool. So any questions about stacks or queues? Any questions at all? Yeah. Okay. So the question was, can I talk about the str function? So in general, whenever you're sort of like overriding a function that comes built in with Python objects, so, okay, first, whenever you create a class in Python, there's kind of an implicit thing here that your class actually is of type object. You're inheriting from object, which is kind of like the Python base class. Although in Python 3, you don't have to be explicit about it. It just happens automatically. And when you're overriding methods that exist in the object class, like the kind of methods that apply to basically every Python object ever, in general, those methods will be prefixed and postfixed with 2 underscores. So that's kind of how you know you're overriding a Python object method. So the string method exists on every Python object. And it's called whenever you print something. When you print an object, it calls the string method on that object to get a string that it can print. And whenever you use the string function like this. So whenever you pass something into the string function to get a string out of it, it calls the same method. So what we did was we overrode it. If we were to not override this and not provide all this pretty printing, we can test it and see what happens. Actually, it crashes, because this line of code here that I added randomly. Okay, so when we print without overriding the string method, Python only knows so much about our class. From the base level object class doesn't know anything about our implementation, doesn't know anything about the stack. So pretty much all it knows is the name of the class and where it lives in memory. So that's pretty much all it can tell us. The default string method will tell you the name of the class and where it lives in memory. So this is a memory address right here, encoded in hexadecimal. So what we do is we override the string method so that we can return more useful information. So now when I run it again, we can see that we can actually see the contents of the stack because we implemented the string method ourselves to return the content, the data that we think is important when we try to print out a stack. Yeah, Jacob.
What is that little segment called at the end of stack object at 0x? What is that right there?
Okay, so this is a hexadecimal string. Whenever you see something prefixed with 0x, that means the following characters are hexadecimal encoded. We'll talk a bit about different bases and what hexadecimal is in a future lecture. But basically, hexadecimal is a number system in which there are 16 digits. So our number system that we normally use is decimal. There are 10 digits. Hexadecimal, there are 16 digits. So it's 101. We're familiar with what that means. But then A. What the heck is A? Well, A actually kind of means like 11 in decimal. So A here is a number. Same with D. D is a number. So if you were to take that memory address and stick it into a decimal form, it would be some big number that would represent where the actual class object we created down here in the test, that's where it lives in memory. So in memory, in your RAM, every item has an address. And that's how you know where the item lives. And so this item lives at OX101A 8DD8, 08DD8. So the thing we created actually lives on my computer in RAM as little electrons and flipped bits at a real address, like a physical address, which is right there. Cool. Any more questions about stacks and or queues? Yes. Because we made this a class and we did it, all correctly like we should, we can import it. So we can now use this stack class in other Python files, which is great. And I was very careful to put all our test stuff in this main function. If we put this test stuff, we could theoretically just put it over here. But that would mean every time we import stack from a different Python file, it would run all this code. But we want only to run this code when we're testing. So by doing this, we ensure that this code only runs when we execute the stack.py script in terminal. Okay, cool. Any more questions? Ignat.
How does the stack work in a processor? Is there more than one stack? Can you access
Okay, so that is a good question. We'll talk about more in depth later, but he asked, how does a stack work in the processor? Is there more than one stack? There is one stack per core, I think, or maybe it's even one stack per thread. The long and short of it is that there's special hardware that makes the stack work really quickly. So there's like an actual hardware implementation of a stack in the processor, the physical processor. That's kind of like a short answer. Can't really tell you the long answer right now, but you can come talk to me later.
What if you have to access like
So he asked, what if we have to access really far data in a stack? In a theoretical stack, in the computer science sense, the one we just made, you can't. In the actual stacks that exist in the real world, sometimes there's methods to access data that's not at the top. And in the one in the processor, sometimes it can just jump around and it gets complicated. Yes, Imad? Right. Oh, okay. So how can we make the tests better than this? How can we make them dynamic? The short answer is that there's different libraries that will help you with that, like different Python libraries. I'm not sure which one to recommend for this case. We would have to do some Googling. But there's ways you can write basically, like they're called unit tests, and they're tests that specifically exercise each function individually, passing it a ton of different data and different edge cases. And there's Python libraries that will help you do that. And in general, that's a good idea. So then you could run this, and you could have it print out the results of 100 tests and tell you if they all passed or not, so that every time you modify the class, you can check and see if it still works the way you think it should. Oh, yeah. Yeah, so if you, instead of running the script like this, if you just run Python 3, you get an interactive terminal here. And then you could do something like import stack. We'll see if that works. No. So there's a little bit more you have to do to make sure it's looking at the current directory and is able to import it. But you can do all this testing in the interactive terminal if you want. OK. Great. So that is it for stacks and queues. There is another lecture this afternoon that Dion will be presenting. And he is walking over here, and he's about to tell you a little bit about it.
Yeah, the lecture is really important. It's not CS related. It's substance, alcohol related. It's really important that you're all here so we can talk about it. It's something that normal schools do, and they will not let you register for classes until you attend something like that. So we're probably going to be keeping track of who's here, who's not here, and talking to you individually if you're not here for that. So that's at 2:30. Make sure you're back at lunch, from lunch by then. Yep. Okay, yeah.
OK. Sorry? Sure.